Hey everyone, and welcome back for another deep dive. Today we're going to be digging into something that's really been captivating everyone's attention lately, and that's AI art.
Yeah, it seems like everywhere you turn, there's some incredible new image or piece of art popping up, and it's all powered by AI.
It really is remarkable to see how quickly this technology is evolving.
Mm.
And, when we talk about AI art, we can't ignore the powerhouse behind it all, diffusion transformers.
Ah, yes, DITs, as they're often called. And they're incredible, don't get me wrong. But one of the big challenges with DITs is that they can be incredibly demanding. We're talking about a lot of processing power and time to create these amazing images.
Yeah, it's like having this team of incredibly talented artists at your disposal, but it takes them weeks to finish a single painting because they're so focused on getting every single brushstroke absolutely perfect. So naturally, researchers are constantly working on ways to make these AI artists, these DITs, work smarter, not just harder. And that's where the people we're diving into today comes in. It's titled Dynamic Diffusion Transformer, or DyDiT for short. Have you had a chance to look over this one yet?
Oh, absolutely. And it's a fascinating read. Basically, the researchers behind DIT zeroed in on two core inefficiencies in the way traditional DITs work. They call them time-step redundancy and spatial redundancy.
Okay, those sound pretty technical. Can you break those down for us a little? What do they actually mean in the context of, an AI trying to create an image?
Sure, so imagine you're a painter, right? And you're working on this incredibly detailed landscape. Now, a traditional DIT would approach this by meticulously rendering every single detail, every leaf on every tree, every cloud in the sky, with the exact same level of effort and precision. And that's where the time-step redundancy comes in. It's like using a fine-tipped brush to paint a giant blue sky when you could just use a roller.
Right, it's about recognizing that different stages of the image creation process call for different levels of detail and therefore different levels of computational effort.
Exactly. And then you've got spatial redundancy, which is kind of a similar idea but applied to different parts of the image. So going back to our landscape example, you might have a really simple blue sky as a backdrop, but then this super detailed forest in the foreground.
So instead of just focusing on the complex parts, the DIT is wasting time and energy on the simple parts too.
Exactly. It's like using a magnifying glass on the entire canvas when really you only need it for certain areas. And that's where DDT steps in to address these inefficiencies. It's all about working smarter, not harder, by understanding which parts of the image need the most attention and which parts can be handled more efficiently.
That's fascinating. So how does it actually do that? Does it have some kind of AI crystal ball that tells it where to focus?
Laughs. Not quite a crystal ball, but the way DDT works is pretty ingenious. It uses two main mechanisms. Something called time-stepwise dynamic width, we'll call it TDW for short, and then spatial-wise dynamic token, or SDT.
I'm already loving these kitschy acronyms, but let's break them down. First up, TDW. What's the deal with dynamic width?
Okay, so think of it this way. Imagine you're an artist, and you're able to adjust the size of your brush strokes depending on the level of detail needed. That's essentially what TDW allows the AI to do.
So in the beginning stages of creating an image, when things are still kind of rough, it's like Data T is using broader, more sweeping brushstrokes, not sweating the small stuff. But then, as the image gets more defined, it can switch to those finer, more computationally expensive brushstrokes to add in the details.
You got it. It's about recognizing that different stages of the image creation process, different time steps, call for different levels of computational effort. So it's dynamically adjusting its width, which is a way of describing how much computational power it's using at different points in the process.
Okay, that makes sense. Now, what about SDT? This is where the AI zooms in on specific parts of the image, right? Like that magnifying glass analogy we were talking about earlier.
Exactly. But instead of a magnifying glass, think of SDT as this highly sophisticated analysis tool. As the image is being generated, SDT is constantly scanning it, looking for areas where it can be more efficient.
So it's looking for shortcuts, but in a smart way.
Exactly. It identifies those easy patches where the pixel values are very similar, like in a large area of blue sky, for example. And it essentially tells the model, you can relax here. We don't need to go overboard with the calculations in this area.
That's so clever. So instead of meticulously rendering every single blade of grass in a field, SDT lets DyDiT focus on, say, the intricate details of a person's face in the foreground, freeing up computational power where it matters most.
Precisely. It's all about being smart with resources and understanding that not all parts of an image require the same level of computational attention.
This is all sounding really impressive.
Yeah.
But does DyDiT actually deliver on these promises? Can it really speed up the AI art generation process without sacrificing the quality of the final image?
Well, that's the million-dollar question, right? And the good news is that the researchers behind DyDiT didn't just stop at theory. They actually put it to the test.
Okay, so how did they do that? What kind of tests are we talking about?
They ran a bunch of experiments using ImageNet.
ImageNet. For those of us who aren't AI experts, can you explain what that is?
Yeah, so ImageNet is like the gold standard when it comes to testing out these image recognition and generation algorithms. It's this massive data set. We're talking millions of images spanning thousands of different categories. So if your AI can handle ImageNet, you know it can pretty much handle anything you throw at it.
Right, so it's like the ultimate test. So they basically threw DyDiT into the deep end to see if it could swim.
Exactly. And let me tell you, it passed with flying colors. When they tested DyDiT on ImageNet, it reduced the computational effort, which we often measure in FLOPs, by a whopping 51% compared to the traditional DIT models.
Wow, 51%. That's a pretty significant improvement.
Oh, absolutely. It's huge. And here's the really impressive part. It managed to achieve this massive reduction in computational effort while maintaining the same level of image quality.
So they didn't have to sacrifice quality for speed. That's really impressive. I mean, that's a game changer. It opens up so many possibilities for artists and researchers who might not have access to, like, supercomputers.
Oh, absolutely. It really democratizes access to this technology, which is incredibly exciting to see. But it gets even better. They didn't just test DyDiT on ImageNet. They also tested it on more specialized datasets. Datasets that focus on specific subjects, like birds or cars or even food.
Oh, that's so cool. So if I want a super realistic image of a delicious-looking pizza generated by AI, DyDiT can do that for me in a fraction of the time it used to take.
Precisely. And the results on those specialized datasets were just as impressive as the ImageNet results. So it's not just a one-trick pony. DyDiT is showing us that this dynamic approach to AI can be really versatile and adaptable.
This is all so fascinating. So we've got speed, we've got quality, we've got versatility. What more could we ask for?
Well, it gets even more exciting. One of the things that really stands out about DyDiT is that it's not just a standalone solution. The researchers designed it to work really well with other cutting-edge techniques that are being developed to improve AI efficiency.
Oh, interesting. So it's like they've taken an already high-performance car and found a way to soup it up even further.
Laughs. That's a great analogy. They've basically added nitrous oxide to an already fast car. And one of the techniques that DyDiT pairs really well with is something called efficient samplers.
Okay, now we're talking efficient samplers. What's that all about?
So, without getting too deep into the weeds, you can think of efficient samplers as a way of optimizing how the AI model samples from the data it's using to create an image.
Okay, so it's like instead of just grabbing information randomly, it's being more deliberate and strategic about it.
You got it. It's about making the whole process smoother and less computationally demanding. And the great thing is that DyDiT is fully compatible with these efficient samplers.
So it's like a match made in AI heaven. They work together to make everything faster and more efficient.
Precisely. And then on top of that, there's Deep Cache.
Deep cache. Okay, I'm intrigued. What does deep cache bring to the table?
Well, Deep Cache is all about smart memory management. It's kind of like, when you're working on a painting and you figure out a really efficient way to paint a certain type of leaf.
Yeah, and then you remember that technique, so you don't have to reinvent the wheel every time you need to paint another leaf.
Exactly. It's like building up a library of techniques and solutions. And that's essentially what Deep Cache is doing for AI. It stores the results of previous calculations, so if the AI model encounters a similar problem in the future, it doesn't have to redo all the work. It can just pull the answer from its memory bank.
That's amazing. Talk about a time saver.
Right. And once again, DyDiT is designed to integrate seamlessly with Deep Cache. So the researchers found that by combining these technologies, DyDiT, efficient samplers, and Deep Cache, you can achieve even more incredible reductions in processing time and power consumption.
This is really remarkable stuff. I mean, we've been focusing on AI art generation, which is amazing in its own right. But when I hear about these kinds of efficiency gains, it makes me wonder about the bigger picture. What does this mean for other areas of AI development?
That's a great question, and I think it's important to step back and look at the bigger picture here. Because DyDiT isn't just about pretty pictures, it represents a fundamental shift in how we think about designing and utilizing AI.
In what way?
Well, for a long time, the prevailing approach in AI has been bigger is better. Just throw more data, more processing power at the problem, and you'll eventually get there.
Right, it's the brute force approach.
Exactly. But DyDiT is showing us that there's a more elegant, a more adaptable way forward. It's about moving away from brute force and towards systems that can learn, adapt, and optimize themselves, just like a human artist would.
So it's not just about building more powerful AI, it's about building smarter AI. AI that understands how to use its resources strategically and efficiently. And that has implications far beyond just the art world.
Absolutely. Think about areas where AI has the potential to revolutionize things, but has been held back by these really intense computational demands.
Like healthcare or engineering or climate modeling. The list goes on and on.
Exactly. Imagine if we could analyze massive data sets in healthcare or run these incredibly complex simulations for climate change research, but we could do it all using a fraction of the computational power that we currently need. That would be a game changer.
It really would. And it sounds like DyDiT is showing us that this kind of future might not be that far off. It's pointing us in the right direction, showing us that the future of AI isn't just about raw processing power, but about designing systems that can truly learn, adapt, and optimize themselves to become more accessible, more powerful, and ultimately more useful in tackling the world's biggest challenges. It's pretty amazing to think that a breakthrough in something like AI art could have such a ripple effect, that it could hold the key to unlocking so much potential in all these other areas.
Yeah, it really does make you realize how interconnected everything is, makes you wonder, like, what other surprises are out there? What other, like, seemingly niche discoveries could end up being the key to solving problems that, we haven't even imagined yet?
It really does feel like we're just scratching the surface, like we're standing at the edge of this whole new world of possibilities.
Yeah.
This has been an incredible deep dive, to say the least. We started with these, really technical details about diffusion transformers, and now we're talking about like the far-reaching impact of this whole idea of dynamic AI. And I got to say, I am so incredibly curious to see where this all goes.
Oh, absolutely. Me too. I mean, that's what's so exciting with this field, right? There's always something new to learn, another layer to uncover.
Well, and speaking of uncovering layers, before we wrap things up, I kind of want to circle back to something you mentioned earlier about DyDiT, like
Yeah.
potentially revolutionizing fields beyond just art. Like, can you give us some more concrete examples of how this work smarter, not harder
Yes.
approach could actually be applied to those other areas?
Yeah, definitely. I mean, the possibilities are really exciting when you start to think about it. Like, take personalized medicine, for example. Right now we're using AI to analyze these huge, massive amounts of genomic data to try to understand diseases better and develop new treatments.
Right.
But those processes are incredibly computationally demanding. They take
Yeah.
a ton of power and time. But with something like DyDiT, we could potentially speed those analyses up significantly, and that could lead to faster diagnoses, more targeted therapies, and who knows, maybe even cures for diseases that have really stumped us for a long time.
That would be incredible. I mean, truly groundbreaking. What about some of the other fields you mentioned, like climate modeling? How could DIT make a difference there?
Oh, climate modeling is a great example. Climate models are notoriously complex and require a ton of computational power just to run simulations and make predictions. But by incorporating those key DyDiT principles, the dynamic resource allocation, we could potentially develop models that are both more accurate and way more efficient. And that would be huge. That would give us a much clearer understanding of our planet's future, and help us make smarter decisions about how to combat climate change.
It's amazing to think that one single innovation, like DyDiT, could have such a massive ripple effect across so many aspects of our lives. It really just goes to show how important it is to support fundamental research in AI and, really explore its potential across all these different disciplines.
I completely agree. And honestly, the most exciting part is that we're still just getting started.
Right.
We're really just scratching the surface. So as we continue to refine these dynamic AI approaches and we start applying them to new challenges, who knows what incredible breakthroughs we might uncover.
It's a future just bursting with possibilities. And for our listeners out there, if you're as fascinated by all this as we are, I definitely encourage you to, dive in a little deeper, explore the world of dynamic AI. You might be amazed by what you find.
Absolutely. Stay curious, keep asking questions.